So let's expand on the two different types of formulas that we come across in chemistry: empirical formula, molecular formula. And as a couple examples, let's just use some hydrocarbons. These are fuels or solvents that's used by humans. This compound here is referred to as methane. Okay, it's the main component in natural gas. And each of these formulas represent methane. Okay? It's just 4 different ways to represent the structure. In our class, it's these 2 that we'll use over and over again. But notice that, like when you draw the structure, oftentimes that does not represent the 3-dimensional shape of the molecule. More on that in chapter 10. Let's look at these 2, let's just look at this representation. Notice that this, yes, it is the molecular formula. That is true, right? Because the molecular formula gives us the actual number of atoms in our structure. The way methane is put together, there's a carbon atom in the middle, 4 hydrogens attached. That's the same formula that I have here. Okay, so definitely the molecular formula. But as it turns out, notice that this is as simple a ratio as you can get between that carbon and that hydrogen for that formula. Therefore, this is also referred to as the empirical formula. And sometimes that's just how it works, that a compound just happens to have its molecular formula and empirical formula being the same. Now, the other example over here, benzene, it's different. One thing, benzene is just a different molecule. Okay, we have 6 carbon atoms that actually form a hexagon pattern. We call it a ring in organic chemistry. Each one of those carbons has a single hydrogen attached to it. And then along the cyclic portion, you see this repeating pattern of a single, double, single bond. Again, don't get caught up in the particulars of the structure. I want to use this to illustrate now the difference. I want to illustrate an example where the molecular formula and empirical formula are different. So again, what I'm looking at here, this is the molecule, okay? If we were to zoom in, benzene would basically look like that. If I count up the number of atoms here, what I have is that formula. Right? I got 6 carbons, I got 6 hydrogens. C6H6. So I'd say the ratio is 6 to 6 in this particular formula. But notice, that is not the empirical formula. If I want to determine the empirical formula, again, that's the simplest whole number ratio. Well, what is the ratio between 6 and 6? That's the simplest ratio, 1 to 1, right? Carbon and hydrogen are coming together in a 1 to 1 ratio in this particular formula. So I would say its empirical formula is just simply C and H. This is an example where this empirical formula does not represent the actual structure of the compound. It's just the simplest ratio. Why do we see this? Well, one thing that happens is that oftentimes in a laboratory experiment, it's the empirical formula that's determined first, and you got to know that first before then you can determine the molecular formula so that you have a shot of actually drawing the compound. That makes sense. We'll kind of see those examples as we move through the next few chapters. Again, right now, it's just establishing empirical versus molecular formulas. Let's practice with a few here. There's a definition still sitting there. Empirical in blue, molecular formula in green. And now notice the way this problem is written. I mean, what you're looking at here, these are all molecular formulas. If we took, a set of, let's just take carbon dioxide real quick. And again, chapter 10, for the test coming up, for this chapter, you do not need to be able to do this, okay? But that's what carbon dioxide looks like. It's a linear molecule. It's got a couple double bonds in there, carbon in the middle. That is the molecule. That is the molecular formula. And I could do a similar thing with every one of these. I could actually draw out the molecule and what it looks like. What the problem is specifically asking for is how do you convert these molecular formulas to the empirical formula? Now, In one of these examples, you don't need to. It's already the empirical formula. CO2, that's the simplest ratio that I can get between these two atoms in the molecule. This is analogous to methane here, 1 to 4, and then the examples I started with. Right? Simplest ratio. Now the other ones, that's not the case. And in some ways what you're doing is you're looking for the lowest common multiple between the numbers of atoms there. Like for example, if I took that formula and divided by 2, I get CH. If I take this formula, divide by 2, I would get C3H6O3. Notice that's still not the simplest ratio. What can I do? Can I divide by something else? I sure can. I can divide by 3. That would give me CH2O. Here, divide by 2, and that gives me BH3. And so these formulas here, I'll go ahead and circle that one. These are all represent the empirical formula for these compounds. Now obviously, this is glucose. It's a really common sugar. I could have just taken this and divided by 6 to get to the empirical formula here. Bottom line is, if you can take a formula, divide all of the subscripts by a whole number, and get some new ratio that's a smaller ratio. And notice there's no fractions here, right? When you're talking about empirical formula, you're looking at whole numbers. And I'll just say this, dividing by 2 or dividing by 3, those two are the most common ones you see over and over again, by the way. That's enough for these molecules or these types of formulas. The next video will focus in the distinction between ionic and molecular.